Yes, today there is a very nice lecture about AdaBoost. Um, so what's planned for today? Yes, it's room S331. Yes, that's right. Room S331. No, I mean strange people are on Zoom. Okay, by the way, let's start because I started streaming. So lecture today is about boosting, and what will I tell? So first, when people, so in the 90s, okay, no, so let's start again. Okay, so uh, I will not give overview. Let's start again. So what is the idea of boosting? So imagine that you need to make a spam filter for email. And so it's like easy to come up with rules that work a little bit. So imagine you have a data set with spam email and regular email. And then you can invent a rule like if the subject is you won lottery you won 5 million in lottery. And so if it contains lottery and subject line or even inside the body, then you have like a bit more than probability 1/2 that this is spam email or inheritance and 5 billion or something. If you see such words, you can do better. And now is the question, imagine that you can come up with many such rules, like rules that work a little bit better than random guessing. Can you combine them into one classifier that's like always correct or has huge accuracy on the training set? And so there is a positive answer by boosting algorithm. So I will present the algorithm. Then we will explain that we can go to zero error with such an algorithm. And moreover, we will explain that zero training error still implies good generalization error. So test set is likely to have small error. But we have two theories to do this using VC dimension and Rademacher complexity. And we will see that the theory with VC dimension is not what we want when we compare it to the details on actual data set. Okay, so there was a problem with dependency on boosting. But just let's go and explain the main idea of the boosting algorithm. So main idea is to maintain a kind of weights on the data points. And in each boosting round, we will select a classifier. So idea of boosting is to have weights on the data points and to select and to update the weights in rounds. So in each round, we will select a classifier that is doing better than random guessing, taking the weights into account. And then we increase the weights of badly classified points to focus on these points and decrease the weights on correctly classified points. And then in the next round, we choose a good classifier according to these points. And in the end, we will output a majority vote of selected classifiers. So this is idea of non-adaptive boosting. So let's just do a simple example. Imagine that we have two features and that training set is like this. So how will we select classifier? So we will select classifier that makes a minimal number of mistakes. And here the weights, initially the weights will be uniform over the training set. And I worked out an example in the notes, so that was good. So here in the example, we can, for example, so what will be the set of base classifiers? It will be decision stumps. It means horizontal and vertical lines. And so here the best line, so we can make a line that only makes 2 mistakes. And that might be this line. So we predict minus here and we predict plus here. So then we will, in the next step, we will increase the weights of the points that are wrongly classified. Sorry, that's 4 mistakes, not 2. So here we will have bigger weights. And here we will have small, here also. And the weights of all other points are smaller. Okay, let's not change, and you understand it. And then we will look again to the best classifier with these augmented weights. So now classifier might be something like this. So this classifier has all the large points with all large weight correct. And so here we have minus, here we have pluses. And I think it's the best one with this classification. So then we repeat the process. So we augment the weights of points that are classified correctly and incorrectly. So the ones that are wrong are now these 4 minuses are wrong, so they become larger. And those who are twice correct become very small. Let's redraw them. And let's do one more boosting round. So now what could be, okay, are there points are twice wrongly classified? No, no points are twice wrongly classified. And so now a third classifier could be, let's think a little bit, where could be the third classifier? Yeah. Or these pluses, yeah, they will focus on these. Yeah, you're right. So if we put it here, then this one is also right, and so we will have a plus here and a minus here. Okay, and so now let's look at the majority vote. We will have some decision then. So we have 2 minus. So where is the decision border? I think decision border will be precisely what we need. Let me try. I will change it if I'm wrong. So here we have 2 pluses. Here we have two pluses. Here we have 2 minuses. Yeah, it works. And so our decision border is right everywhere. So this is the idea. Okay, so now here is the algorithm in detail. So what's the input? A set of B classifiers. Here we have decision stamps, 2 dimensions. By the way, the labels of classifiers always -1, +1. It will be very useful this lecture. We need to know an amplification factor, how much we change the weight, and it's a number between 0 and 1. By the way, it's not in most books. I simplified notation for this presentation of algorithm and the proofs that we need. But okay, it's equivalent in it. Okay, in this rule there are minor variants, but not important. Okay, so yes, a number of rounds and a training set. And so initially the weights are all 1, and then for number of boosting rounds many times, we select base classifier, so it minimizes in the set of B classifiers. So it selects a classifier H and B, such that the sum of weights of wrongly classified points is minimal. Then we update the weights. So if point is correctly classified, then this exponent will be +1. So note y is -1 or +1. HT will be a class. So B contains classifiers with binary values, not regression like previous lectures. Set of B is that's right. That B is a subset of -1 + 1 in the power x. Okay, it's unreadable, but most people already know. So okay, for those watching on YouTube, let's write it clearly. what I want to say is that we have B is a subset of functions -1 + 1 to the power x. Okay, so we select the H and B that minimizes the sum, then we update the weights. And so here we have two values that are both -1 and +1. If they're equal, exponent will be positive and the weight decreases, otherwise it's negative. And then the output is majority vote of selected classifiers in each of the T rounds. So that's it. Okay. Now, okay. And now there is a nice theorem that promises us, like, if the weights are not too big, if the sum of wrongly classified weights are more than majority, if we can achieve less than majority of the weights here, then we will have exponentially fast convergence of number of error empirical risk will converge empirically fast. So let me write down the theorem and have a careful look so that I don't make any mistakes. So theorem here. So first let's have you came. Yeah, okay. Yeah. So first let us use this notation that we had last time again. So when we have a vector of weight and we say that we sample I according to W, probability of certain event, E of I is just equal to the sum over. We just normalize the weights and treat them as probabilities. We did it before in online learning. So if W is just a vector of non-negative numbers, then this just means, okay, let's write it because this is equal to the sum of Wi for which EI holds divided by the sum of all W. Okay, and so now the theorem says that if so we choose a specific value so for all gamma bigger than 0, if A is equal to, and then we have some expression 1/2 plus gamma. Gamma will be called the edge, and in each round, round T, probability of picking correctly. So if the selected classifier makes small error, so it is 1/2 minus gamma. So gamma is called the edge because it does better than random guessing by the constant gamma. And if these two conditions are satisfied, we get exponential convergence of the error. So, and then empirical risk of S. So S is a training set. Of output is smaller than exponent -2 gamma squared. So T is number of boosting rounds. So that's theorem that guarantees very fast convergence. So theorem in itself, it's nice to know, but it's not so useful. But the proof is useful when we think a bit further, when we make risk bound and analyze things a bit further. So, okay, proof is just 2 steps. We will make an upper bound on empirical risk. And then we will say empirical risk is upper bounded by the sum of weights and round T plus 1. And then we will prove, like we did in online learning, that sum of weights decreases in every round by constant factor. So that's 2 steps. Okay, and now Step one, let's make an upper bound for empirical risk. And the idea is extremely simple. So the function, indicator function, this is one if t is at most zero, it's zero otherwise. And this is bounded by a to the power t. So, right, if t is positive, no, that doesn't work. Sorry. If t is strictly bigger than zero, this is zero, and it's always true. And if t is at most zero, this is one. But since a is smaller than one, this will be at least one.
Sorry, t is the number of standard.
T is just any real number. Oh, sorry, yeah, I have let's take any real number r. Okay.
Okay,
Yeah. So just r and any real number here. Okay. So now let us use let us call this the function g. So let us have no, I won't need the space. Now is the question, can we use this technique to bound empirical risk by n times, just empirical risk bounded by sum of all weights on round capital T. So, sorry, the sum of all weights on the round capital T plus one.
In the statement of the theorem, so there is a probability, and I distributed as V as W at step T.
Yeah. So we normalize. So what does it mean? We normalize W and get probabilities. Okay. So yes, I will use helper function G at just the sum of all H. So let us have G of X equal to H1 of X plus HT of X. And then wrong classification means this. So if G makes an error, then this, well, we should have strict inequality, but I will make an upper bound on empirical risk. So I will use something. So if point XY is wrongly classified by the output classifier, then this value is equal to 1. And we know that this is equal to y g of x. Okay, so now we can write down an upper bound for empirical risk. Rs of output is bounded by, okay, let's take multiply by n to get rid of all annoying things, is just the sum over all I, a of yi g xi. Smaller than n. Oh, and by the way, so what can we say about this thing? It's equal to something we need. Yeah, I already said it. So it is the weight after all the updates, because we start with 1, then we multiply all the updates in each boosting round. So this is equal to sum over all I smaller than n w t plus 1 of I. So this is the first step of the proof. We make an upper bound on empirical risk. Oh, and I forgot that here now. So that makes, oh, no, doesn't work. Okay, probably I forgot something somewhere.
But I think that why do we think that a to the power of y I times g of x I equals w?
Yeah,
We classify with base classifiers, right? But here we have like contradiction.
so G is sum of base classifiers. So here is sum of base classifiers times y.
Okay.
Yeah, and then
But is it, no,
Yeah, I think I just forgot the end here, the theorem works, but okay, we will just see it in a second. So that's our first goal. We get the upper bound here. Now we prove that the sum of weights decreases exponentially fast. So we want to prove that sum I smaller than n of w t plus 1 of I. So we want something for this. Okay. And this is here we have two groups of weights. There are weights of classifier that are correct on the new on the HT, and these are incorrect. So let's group them. And so we know that for correct classifiers, WT plus 1I. So if I point is correctly classified, its weight decreases. So WTI. So if I point is correct, otherwise it's incorrect. So we can write this as so this is sum over, so we will have two sums correct, as I already sent, AWDI for I such that xi is equal to y. And here we have the opposite, 1 over a times WTI, for which xi not equal to y. Okay, what do we have here? We can view this as convex combination. So we can view this as something of the so the right expression. So we want to have an upper bound for it. We can view it as alpha. So some weight factor times a, or let's say 1 minus alpha, plus alpha times 1 over a. Because here we have sum of weights of something, and here we have some of the other weights. So here the two coefficients for a and 1 over a, they sum up to 1. We take convex combination of a and 1 over a here in this expression. And so when we want to maximize it, so recall a is smaller than 1, we take maximal possible value of alpha. And this value is, what is it? Well, there was better bound. So think about it. Better. So look at the statement of the theorem. Yeah. So here we take W as a vector. Oh, sorry, I forgot the index t there. So W, the weights at time t. Okay. Yeah. And so here we do the same thing. We look at the weights at time t. And we check this. So we understand that alpha is at most 1/2 minus gamma. So we see that this is bounded by 1 minus, and here we have 1/2 minus gamma times a plus 1/2 minus gamma 1 over a.
Would you please explain once again why weights are sum up to 1?
Okay. So every classifier has a weight. Every data point has a weight. There are two types of data points: the ones that are right at HT and the ones that are wrong at HT. And so every weight in this sum either appears here or here. Yeah.
So we assume like that's not just numerator, but the whole fraction is like convex combination.
Yeah, exactly. And so we will take largest possible coefficient And this will be 1/2 minus gamma to get upper bound. Okay, and now it becomes clear. So what do we get now? Uh, so this is equal to 1/2 plus gamma times A plus, okay, the rest remains the same, 1/2 minus gamma 1/A. And now look at A. So how we choose A here in the theorem, we get 2 times the same thing. So it's equal to 2 times square root 1/2 plus gamma, 1/2 minus gamma. Okay. And now the only thing we have to do is prove that this is smaller than -2 gamma squared. Sorry. Yeah, something like this. Yeah, and then it's not so difficult, right? Because here we have this special product. I hope it's still, is it still visible? Okay, so this becomes square root 1 minus 4 gamma squared. And then we again use 1 minus r smaller than exponent minus r. Right? And so this is okay.
We also have C large statement exponent minus 2 gamma squared.
Yeah, this is for every round. So when we go in one round, the sum of weights decreases by this factor, which is bounded by this thing.
And then we will have
Yeah, we have this
the
E
product.
times. Yeah. And so, and I started with this inequality. Oh, wait, and so I also, to get this, I need to multiply with initial weights. So I don't have n here. So my original writing was correct. Yeah, of course it's correct. I copied from the notes. So why did I start doubting? And so we started with NRS is bigger than this. And then we say that this is smaller than sum of initial weights 1i times exponent minus 2 gamma squared to the power t, because we have t round. And this will be equal to n, and then the proof finishes. So n drops on both sides.
So we have the sum of weights because we divided by it in like the middle of the product.
Yeah, here.
Could you please explain once again why we have upper bound on alpha, like 1/2 minus gamma?
Okay, so where is alpha? Alpha is here, right? So alpha is this sum divided by WT, and we put 1 over, without 1 over A. Alpha is fraction of weights of wrongly classified, but fraction, that's precisely by this definition. Yeah. Okay, so that's cool, because how many rounds do we need to have 0 error on training set? Okay, that's just silly calculations. So we need to have this bound smaller than 1 over n, and it will be then ln n divided by 1 over 2 gamma squared. So if t is strictly bigger than this, then we train till 0 error, which is pretty cool. I mean, if you have reasonable gamma, of course. So indeed, if you can each time find the rule in your emails that has error at most 0.4, then you need 1 over 200 times ln of your size, which is reasonably small.
Yeah,
If
it's
it's down,
50,
yeah.
it's no problem. Because you said like gamma is 1/10.
Gamma is 1/10, but we have gamma squared here.
So it will be in the denominator.
Yeah. So it becomes 100, 1 over 200.
No, it's not 1 over 200. It's 1 over 2 times 100. And then it's
Yeah. 1 over 2 times, but yeah, 1 over 2 times, yeah. Yeah, 50, yeah, you're right. Yeah, yeah, even better. Yeah, of course, yeah. 50 times Allenham, so if n is 1,000, that will be like, whatever, also not so big.
Why,
250 rounds or something.
why we have to zero in trade there? So if we substitute like this t, we have that.
Yeah, yeah, but
empirical-
empirical risk is a multiple of 1 over n. So it's a number of wrongly classified points divided by n. So if the upper bound is smaller than 1 over n, then only possible value is 0.
Okay.
Okay. So yes, this is first goal. And so now I will explain what is AdaBoost. And normally when people present it, they will normalize the weights, but I will not do it because it just extra back and forth, a waste of time. So what's the idea of AdaBoost? Is not to output a majority vote here, but if there is a very good classifier, to give it larger weight. And the weight we will get by making adapted increases here as well. So I will now add an extra line. I was clever. I have already left some space. And so we will say that AT is equal to square root of epsilon t divided by 1 minus epsilon t. Epsilon t will be the fraction of weight of classified points. It's the error. So epsilon t is this probability I according to WT that h of xi, ht of xi is not equal to y. And then the rest is the same. So update, well, very similar. T plus 1 of I is WTI times AT, and the output. So the weights are the logarithms of AT. So the output is x goes to the sine of 1 over this and 1 over A1 times H1 of x plus and 1 over A2 like this. Let me check that I'm not lying to you. So your Ln is like this, right? So again, if epsilon is very small, it means that A is very small, and it means that coefficient becomes very large. So now for the theorem, we will get something better. So we will have that empirical risk of the output is smaller than the product of the epsilon t's in the rounds. And that means that if this, so this is equal to epsilon, we don't need it anymore because I've written it here again. So this is our theorem. And proof is very similar. So the only step that changes is here, right? It becomes actually easier. And because here we have exactly equal to epsilon t, so this calculation with convex combination consideration we don't even need it. So I can let's just write it here. So we have just 1 minus epsilon t here And here we have epsilon t. Okay, and now there is important remark. So how did we choose AT? And so there is special value AT, square root epsilon t, 1 minus epsilon t here. So well, there's the value that AT, that this value of AT optimizes the sum, minimizes the sum. Okay. This is an important remark. Okay, and then we just work it out in a similar way, and we get this product. And you see from the proof that if we bound epsilons by 1/2 minus gamma, then we get the same result again with exponent minus 2 t times gamma squared. Okay, so now, so this non-adaptive boosting algorithm, it was like culmination of long research on open question on cryptography. Like the question was, if you can guess a little bit of a password in little steps, can you break the full password? And the answer was yes. And so they understood that like some weak notion and strong notion of security were equivalent. The original proof was very difficult, like a full chapter in the book. But then somebody with background from online learning made this elegant proof. And then 10 years later, people were surprised that it's actually able to beat neural networks. Like the adaptive variant was able to beat neural networks and SVM on some data sets. And it was, yeah, so I already learned all this, and it was surprising that it actually useful. Yeah, so, but then to get for this notion of cryptography, they actually needed generalization error. So they needed a risk bound, and they took it from VC dimension. I will explain it in a minute. First, I will explain something else while we have this proof. So how can you invent this algorithm? There is like a similar way that people realize they could have invented much earlier. So there is an algorithm called coordinate descent. And what is happening here is we start from upper bound on, where is my upper bound? Here, this is, well, this is an upper bound on the empirical risk. If you apply coordinate descent, it's like the, just a simple algorithm for convex optimization. And if you apply coordinate descent, you get exactly this boosting algorithm. So, okay, I will now say what is coordinate descent and why it's exactly the same. But maybe if you have course on convex optimization, maybe it's already there. I don't know.
We can previously with that. And this was the time 4 years.
Okay, yeah.
But I don't really know how it's constructed.
Yeah, because it's no longer used coordinate descent. Component need this
Yes,
descent. I don't know, but something like that. Yeah, but it's not used. I don't know any other application. So just old people who were already old at that time knew that they should have known it. Okay. So, yes. Okay, let me double check. Yeah, first I need to say what is coordinate descent. I can now delete this thing.
both of these algorithms are non-adaptive, right?
No, this is AdaBoost here. Sorry, I didn't change the name.
Yeah, but you said that.
Yeah. And AdaBoost is coordinate descent. So the one that works in practice is old algorithm for convex optimization. Okay, so coordinate descent. That is function L. With we will use M inputs and it will go to R. And then let's start with alpha is 0 to the power M. And then repeat. Repeat 3 times, two rules, select coordinate, and we take the coordinate with the biggest gradient. So we compute the most negative partial derivative. Choose S smaller than M, so that dl xs of alpha 1 alpha s alpha m is minimal. Oh, I'm stupid because I don't need the space. Okay, and then the second one, then optimize this coordinate. Or just choose eta. Now alpha 1 alpha s plus eta alpha m is minimal. So, okay. Let's coordinate descent. And now let us see that this is the same. So we can do it by okay, if there are ties here, then we assume they're broken in the same way as the ties are broken here when we minimize each other, when we choose HT. Okay, so let us we need a few definitions. So we use a set of base classifiers. Let's just say that B is finite. B is equal to B1 till Bn. And AdaBoost produces a convex combination, a linear combination of these values. By the way, we can assume that all coefficients are positive because, well, assuming AdaBoost works normally, we will have epsilon strictly smaller than 1/2. That means that AD is smaller than 1, and all these coefficients are positive. But okay, we don't need it, just a small remark. So we will have B equal to B1 till Bn. Yes. And then so we are optimizing the coefficients of these functions. So so at any moment we can consider the function g of x is equal to so let us use function b of x equal to b1 of x till bn of x. Okay, then we can write g of x, it's equal to, there's a function g we already used before this, so the sum of, so g changes over time now. So it will be the dot product of alpha and b. And so now our objective will be the upper bound we had. Let me be careful here.
So now we're trying to obtain
Yeah,
the weights of adaptive boosting with coordinate descent.
yeah. But I need to be a bit careful. So let us just follow the notes, and I will say that L of So L of vector A, so our objective function, which is upper bound on empirical risk, will be exponent minus yi alpha times b of x. So note I used different base here, but this base is just because I was using lns here. That's why I choose exponential base. Before I had, for non-adaptive boosting, the coefficient A was fixed over the rounds. So now I need some base here, and I choose exponent because I have natural logarithm here. So we are using computer science convention. Log means log with base 2, and ln means natural logarithm. It's for people on YouTube. Okay. Yes. So, and now we will apply coordinate descent to this objective function, and we start with all alphas being 0.
How this objective is connected with the bound for non-adaptive boosting? In that bound, we have gamma and number of rounds.
Yeah, so if you choose all epsilons equal to gamma, then you get the same, then adaptive and non-adaptive boosting are the same. But adaptive boosting is a bit more clever. Like if the classifier works really good, then epsilon will be small and put higher weight.
Okay, I see, but the objective is like, what is the intuition of having this?
Yeah, so we will say that after t rounds, we will have the coefficients alpha to be equal to okay. Yes, what we will say is that the alpha coefficients are equal to the logarithms of the ATs. That's what we are going to prove now.
Oh, okay.
So we will say that coordinate descent. So in the S round, it will select coordinate S that corresponds to the same classifier HT here. And eventually we end up with the same coefficient. And one can also prove that L of alpha is upper bound on empirical risk. So empirical risk is an annoying function because if we change the alphas, there is this does not continue in alpha. But this upper bound is smooth in alpha. That's why we like this bound. Okay. So yes. But the proof is just a silly computation. We just have to check partial derivatives, and we will see that they are a linear function of the epsilons with the correct sign, with the correct dependence. So the sign is correct on the epsilon. Okay, so just let's compute the derivative. This one I should also keep. Oh, let us just write down the derivative. L alpha. Yeah, I should better write not x, but alpha. So, oh, and I forgot the sum over I here. Overall, yeah. Okay. So we will again have the sum over I. Then the derivative of exponent, that means exponent stays, but the coefficient goes in the front, and we get yi dxi.
The objective we have alpha I.
No,
So not alpha.
but we check the mode. Sorry, I didn't listen to you.
In the objective we have alpha I, not just alpha, right? So L of alpha is
So this is a vector, this is a vector, this is dot product.
okay.
So it's I less or equal than M. Because
Yeah, sorry, and here I made a mistake. So sorry, this was not a mistake, like this. So when we take the derivative to alpha s, then we get coefficient, which is bs xi. So B is this vector.
So in index under the sum B less significant than M. Okay? Because you put M first,
Yeah, I from 1 to n.
but there you use the M.
Yeah, m is number of base classifiers.
Uh-huh.
That's the number of coordinates in coordinate descent. R goes from m.
And it's number of
Yeah.
data points.
So we have s
Uh,
bounded by m. Yeah, it's maybe annoying. I should think about changing that, but then I will forget half of the indexes and the notes. It will be okay. It doesn't matter. Yeah. So m s is bounded by m. So this we all agree that this is gradient, right? Okay. So now if we agree by induction that for up to round t, small t, they did the same thing, then we can believe that this is equal to the rate WTI. And then we need to complete the induction. So what is this? This is plus or minus 1, depending on whether BS classifier is right on point I. And so we can write this. So what we get here is probability. So this is equal to the sum of all weights where BS is right, minus the sum of all weights where BS is wrong. This is very similar to what we had here. And so it just sum of all weights where BS is right, minus sum of all weights where BS is wrong. So, but we know that so it is equal to sum of all weights on previous round EI times oh, sorry, what did I say? So it is epsilon t, fraction of points that are right, minus 1 minus epsilon t. Here, I mean the error for classifier S. I should use another method for it. Sorry. So this is equal to probability BS of xi, not equal to there are no i's here. And, oh, sorry, there are i's. Okay. Minus you have a minus for classifiers that are right and a plus for classifiers that are wrong. BS xi not equal to y. Okay. But this is just 1 minus this probability. Right? So we have minus 1 plus 2 times this probability. This is equal to coefficient 1 minus 1 plus 2 times probability that BS is right. BS is wrong. So when is it minimal? If this probability is minimal. That's the only thing that depends on S. So we will see that coordinate descent selects base classifier that minimizes the error here. So we see that HS is equal to BS in round S. So HS here, selected here. Okay, sorry.
Isn't so the minimum of this probability is probably less than 1/2, yes.
Yeah.
And that means that it's gonna switch its sign from one to negative.
So this probability is less than technically less than 1/2.
Yeah, that means that this term is less
This
than
gradient is negative.
Yeah,
So
but how can
That's also what happens typically in AdaBoost. Coefficients goes from 0 to 1. So in AdaBoost, we have these coefficients to be positive. So the total coefficient for each classifier typically increases.
Yeah, but I
So
mean,
it's normal.
I mean, if our if our sum of the coefficients is negative, then it's not like it's not the we won't minimize within this formula, because if the left term is negative, we need to maximize the right term.
Sorry, I don't understand. So we choose the gradient that is most negative doing, and then we so that's the plan. Choose coordinate for which partial derivative is goes down very steeply. Maybe it makes sense to put absolute value here and maximize absolute value of this function, and then you can choose the direction.
So I'm just maybe I don't get. So this formula it is a formula for
partial derivative.
Okay.
Yeah. And we want the most negative. Yeah. But okay, there is some criticism. Here I say, what if the derivative is very positive? Then we would also want to update this coordinate. Then we make it grow. But in this context, it's a typical situation. So maybe I just took it from Mori's book. He also says most negative, but it doesn't make sense. Okay, but let's not waste too much time on this, because there are much more important things to say. Sorry, I need to say that the value will be optimized. So what is the value of eta to be chosen to minimize L? And if you write this out, then we will come up basically with this. So if we compute this value, you see that the thing that depends on eta is proportional to this thing. And so we want to optimize. So the choice of eta is directly connected to this AT here. I will skip it because otherwise I lose too much time and I cannot speak about other important things. So just it's in the notes and also in more book about AdaBoost. Okay. So what else? So tactical implementation is decision stumps. It was 20 years ago, and now they use a little bit bigger decision trees as base classifiers. And note that if the data set is fixed, you only need finitely many base classifiers because they're non-equivalent. So in every for every coordinate, you just have finitely many. So if you have d dimensions and points, d times n plus 1 classifiers are enough. So you can make a list of them, and then the implementation is very fast. Okay, but now let's speak about a real interesting part about the rift bounds. Okay. So first, first thing is we can make rift bound with VC dimension. But there is a small problem here. So we are learning linear combinations of base classifier, in fact, convex combinations. So let us assume that this weak learning assumption from the theorem holds. So let us have a training set for which. Okay, why do I explain about coordinate descent? I forgot to tell you the important thing. So you can change. So here we start from the upper bound of empirical risk. You can change the upper bound. Then by applying coordinate descent, you get a new boosting algorithm. And we will see inside this boosting algorithm, something magical happens that not understood. So you can change this upper bound and take with you this non-understood thing. And this is for seminar and homework. Okay. Yes, but then let's speak about VC dimension. So what we are learning here is linear combinations, but in fact we can say convex combinations. Why? And if these epsilons are smaller than one half, then all these coefficients are positive, and we can scale them by the sum of these coefficients. So then we get a convex combination of base classifiers. So linear and convex combinations, thanks to the sign, is the same thing. But we don't get a generalization bound with VC dimension. Because in homework, we proved that VC dimension of linear combinations or even convex combinations of decision times, even in one dimension, is infinite. So we don't get a risk bound. The only way to get a risk bound is if we are a bit more careful and remember that we only use T-boosting rules and have a bound that depends on the number of rounds. So in one of the seminars, we made a bound on VC dimension of linear combinations of classifiers after taking sign. And this bound was we got an upper bound. So let us write convex E of B. Just all the classifiers you can get by, I don't need to write it, okay? You remember from seminar. Okay, that's right, it doesn't take long. So this is equal to x goes to the sign of alpha 1 b1 plus, need to apply argument. Plus alpha t bt of x. And so, well, what are conditions? Alphas are convex combinations, and B1 till Bt, they are in the class B, and alpha are non-negative numbers, and alpha 1 plus alpha t is equal to 1. Okay. And then we have that VC dimension of convolution of the elements is bounded by T times VC dimension of B times ln T. And so probably there was some coefficient like 6 or something. And I don't remember ln or log, it's not important. Some linear, let's be safe and put 20. That doesn't matter. And this bound is more or less optimal. So there is a lower bound also for decision trees. There is a lower bound that has the same but without a logarithm. And here's some small coefficient, 0.1 or something. This lower bound we didn't prove, but it's boring. You need to construct sets and so on. So what does it mean for risk bound? Is that the more you boost, the bigger get your bound. And so risk bound has two components. So risk bound of output is bounded by empirical risk of output plus, and then regularization term. I don't remember it. Here is it. So it is square root k over n. K is VC dimension. Ln En over k. So this is bound of chapter 11, which was slightly better than the one of chapter 9. So we got this with Rademacher complex. But okay. And then this fluctuation term, ln 1 over delta divided by 2n. But this is small, that's not waste time on it. Okay, k is here VC dimension of the VC dimension of class to which the output belongs. And so we see that k is proportional to the number of boosting rounds. So logical conclusion, if output makes zero error, then we should stop boosting because we are increasing this term. If we continue boosting, then this error will grow. But then there is a famous paper and it says it's very good to keep boosting. There is a curve that goes down and typically extremely fast down, not 200, but after 5 rounds, you are at 0 error. But then on the test set, error was 10%. And they continue boosting 5 more rounds, and then error drops to 5% and then take more or less stable. And then after 1,000 rounds, it increases a little bit. So when you boost until 0 error, you should continue boosting. And that means that this is very bad bound, even though this bound was crucial in solving this cryptography problem. So they realized that we need few rounds and it was small enough to guarantee convergence on their specific problem. Okay, so then people realized that they had, so people look to the data and they see that there was some margin was playing a role. And so they switched to empirical margin risk. And then we can make a new risk bound with, let us get the risk bound that we consider. So for any distribution, we are interested in sign of G. So G is this linear combination. Sign of G of X. So it is bounded by empirical margin risk for some margin rho of G plus 2 over rho times Rademacher complexity of the class function G belongs to. And so we can say, as I already explained, we can say that G is a convex combination of the base class, and then plus Ln1 over delta divided by 2 over n. Okay. So
you have a margin assumption on our data.
yeah. So here now we have bias complexity trade-off as usual. If we choose small margin, then it means that this value will be lower. It's likely to be lower, but overfitting term is likely to be higher. And so now we can understand a little bit what is happening. And note that, we also proved, well, I skipped it in the lecture, but probably you read it in the notes and also you need it in the seminar. So what happens with Rademacher complexity if we take convex combination of the class? Do you remember this? The thing is that the Rademacher complexity doesn't change. It's the same, because you should think about the definition. What is it? It's a maximum. So empirical Rademacher complexity of, oh, you got it. So we have convex of B, and this is expected value over sigma, where we take a maximum over F in convex B of, and then something here, right? But when we take F in convex B, then we have extra parameters over alpha, and we know that whatever is here, we will reach it in one of the extremal points. And so that means when we take maximum over convex B, it's just we take the maximum over B. And so Rademacher complexity doesn't change. So we don't even need, so it doesn't matter how many rounds we take here. What does matter is this complexity bias trade-off. And so we see that even if empirical risk is 0, there is no guarantee that empirical margin risk is 0. And that's why continuing to boost helps. And now there is even something even nicer. We can actually prove that empirical margin risk goes to 0. for quite a big margin. So I will prove this. I should this 8 minutes, but it's not so difficult to prove. And then okay, let's quickly explain why this is true. Or just let's write the statement of the theorem. I should write it there. So there is theorem. So sorry, I need first the definition. So what is the weak learning hypothesis? Weak learning hypothesis says that not just let's do it from memory. So given a data set and a set of base classifier, base and x1, y1, and so on, xn, yn. So we say that the learning hypothesis is true if for every vector w, then we can have epsilon, sorry, and we also need gamma bigger than 0. And the weak learner classifier for certain value of gamma means that for every set of weights, you can have error smaller than 1/2 minus gamma. Natural thing, right? So this is the gamma weak learning condition or something, or hypothesis. I forgot how it's called. It means that for every w, then so for any convex combinations over n coordinates, probability I over, so there exists the linear so there exists base classifier. There exists F and B, so that probability Fxi not equal to yi is smaller than 1/2 minus gamma. So just think about the emails. We have that the weak learner hypothesis is true for our training set with a gamma equal to 0.1. If we always have in our set of basic rules for span, we can always find one rule that has accuracy 0.4. Okay, now I can say what is theorem. If weak learning, so gamma weak learning hypothesis implies that very easy empirical margin risk of S, so let's call this S of output let's try to quantify it. So for every gamma bigger than 0, strictly bigger than 0, there exists R strictly smaller than 1. So that weak learning, the gamma weak learner hypothesis implies that empirical risk of S of output after T rounds is smaller than R to the power. So that's it. And so we have an R strictly smaller than 1, so that when we keep growing T, we decrease by R to the power T. Before we had R equal to 1 minus 2 gamma squared, something like this. Sorry, e to the power minus 2 gamma squared, something like this. And now we just have one R, and this R can be much larger than this value, so the decrease might be slower. Okay, I will skip the proof of the theorem because it just follows the proof we had before. There is just a little bit of slack everywhere where we have where we have a risk bound. We have like a linear correction for the margin, and this will go inside the other bounds. But it has amazing corollary. It means that AdaBoost in the infinite for infinitely many rounds in the limit, AdaBoost always find a classifier for which the margin is at least gamma. And this has another corollary.
And here we have just empirical risk or margin.
Empirical risk. Sorry, it should be, sorry, I mean empirical margin risk. Yeah, sorry, thank you. Yeah. So empirical margin risk converges to zero. It has a second corollary. It says that if the gamma weak learning condition is true, then there exists a classifier that classifies all points with margin gamma. It's a stronger corollary. So there exists such a classifier, and AdaBoost finds it. But now there is
like limit or some
in the limit. Yeah, it finds it in the. So if we keep going, so we have finitely many. Let's think that B is finite. Then we keep going in rounds, and these coefficients. So the total coefficient of given classifier keeps growing. There is an exercise like this, where you have to evaluate the margin and prove something about it. So the coefficients will keep growing, and they will converge to a classifier with margin gamma. And so, but then the question is, if we fix the data set, does AdaBoost, it finds a large margin, does it find the maximal margin? That would be really cool. And this is false. It doesn't find maximal margin, but because we can prove that the largest gamma for which the weak learning condition holds is equal to half of the optimal margin. And this is direct consequence of minimax theorem. So, but I don't have time to go over this proof. I will do it next lecture. But then it means that the next lecture I will not be finished. So I will use this extra lecture then. So it will be 30. Okay, but just I will explain. But I will tell you what is the statement of this last theorem. Because it's kind of like you write the proof is like you write everything down and suddenly there is minimax theorem. It's complete. So there is another theorem. So equivalent. The following are equivalent. So weak learning, the gamma weak learning hypothesis false. So equivalent for the triple B, S, and gamma. Weak learning hypothesis false, and there exists alpha, such that alpha times for the classifier, such that x, well, the regression function x goes to alpha times b of x, satisfied has margin to gamma. But we should say that this is L1 margin, because I didn't define carefully what is L1 margin. So what is L1 margin is the following. So we assume that here alpha, the coefficient sum to 1. So here the delta n, I mean positive, non-negative coefficients that sum to 1. So there exists alpha in delta m, such that x has L1 margin gamma. And what is L1 margin? Okay, sorry, and I should divide by the 1 norm of alpha here. And so our L1 margin of some function g a regression function here to R. It's just the minimal value is just the minimal value over the training set and of what you want to be G X. So that's I have to write it higher. It's not really. But what's the margin is natural thing, right? So we have a regression function.
That's L1, so
Yeah. So a regression function for which we use the sign for classification. And then the margin tells us how close we are by zero. So we assume that G is always right. The sign of G is always right. Then here we get a positive number. So here we have L1 margin. And so when we have and what we say is that if gamma weak learning hypothesis holds, if and only if there exists an alpha such that L1 margin is at least 2 gamma. At least 2 gamma. So what does this say? So L1 margin, we are interested. For AdaBoost, what is the closest point to being misclassified? How far are we? And we do it in some reasonable way because we normalize by the norm of coefficients here. When G consists of base classifiers multiplied by coefficient that sum to 1. We take convex combination. Okay, and this is amazing. So it says that so the best gamma for which we have weak learner hypothesis is half of the best margin of classifier. But AdaBoost is guaranteed to find classifier that has half that. So this theorem implies that AdaBoost finds a classifier that has at least half, whose margin is at least half of the best margin. And so can it be improved? And the answer is no. So there exist counterexamples, but they're pretty big. So some mathematician found this. So then is the question, okay, minimize L1 margin, it's linear programming problem, can be transformed to this. And so if all of this theory makes sense, all of these risk bounds, they fundamentally rely on L1 margin. I went a bit quickly over it, but before we apply the risk bound, we need to use a suitable scaling of coefficients. Otherwise, I have other factors there, and I forgot to tell you, but you need to scale coefficients in this way to get a good risk bound. It's kind of natural thing, and it gives good risk bound. I went over it too fast, so sorry for being confused. But okay, so. Yes. So if all these risk bounds make sense, then this algorithm that directly optimizes the margin should work better. But if you do this on data, you see it work worse. And there are real strange data sets where AdaBoost produces a classifier for which for each point in the data set, you get worse margin. But on the training set, AdaBoost works better. So there is a reference to the paper. I checked myself, ionosphere data set, and they say it in the paper. Each point produces worse. So why is this suspicious? Like AdaBoost focuses on the worst point that provides the worst margin. There it will keep increasing weights that classify this point correctly, and then it moves to another. So it focuses on a few bad points. And this is bad because you want to have a classifier that like takes all the points of the data set into account. So it's normal, but when your data training set, when the margin of AdaBoost is worse for every single point in the training set, then you expect worse classification on test set, but it's not true. So there is something inside this AdaBoost algorithm that's no theory can explain, or at least that's what Mori writes. So mystery is happening there. Okay, and by this I will end the lecture. We started a few minutes late. Yeah, exactly.